Welcome in Dark Core. A quiet gas cloud on the galaxy's edge just revealed a cosmic surprise. China's fast telescope mapped G165 50,000 light-years out and found tangled supersonic filaments shaped not by stars or gravity, but by turbulence and magnetic fields. No cold gas, no chaos, just warm, untouched matter in its purest form. This could rewrite how we think structure forms in the universe. Keep watching this video. We'll explore more about this topic. What was found G165 is what astronomers call a very high-velocity cloud made mostly of atomic hydrogen and moving through the outer regions of the Milky Way at around 300 kilometers per second. It's located far from the galactic disk, roughly 50,000 light-years from Earth in a region largely free from stellar interference. This isolation makes it a useful target. Unlike other regions influenced by radiation, supernovae, or gravity wells, very high-velocity clouds like G165 allow scientists to study how gas behaves in a relatively quiet environment. Previous observations of similar clouds offered limited resolution. They generally showed smooth amorphous shapes. But when researchers pointed the 500-meter aperture spherical telescope fast at G165, the picture changed entirely. The 21 centimeters hydrogen line data revealed a surprising structure, a complex web-like arrangement of gas filaments stretching across multiple layers of velocity. These weren't random strands. They were coordinated, twisted, and even intersecting, forming what looks like a three-dimensional lattice. The gas in it also showed supersonic motion, meaning it was moving faster than the speed of sound in its medium. This was visible in the form of subtle fluctuations, wiggles, in the spectral data. Another surprising element, the cloud is dominated by the warm neutral medium or W&M. This is hydrogen gas at temperatures around 6,000 to 10,000 Kelvin. There's little or no cold gas present. That's significant because it suggests it is in a very early stage of evolution, one in which gas hasn't yet cooled enough to condense or collapse into stars. Why it matters, conventional models often place gravity at the center of structure formation. It's gravity that pulls gas together, increases density, and leads to the eventual collapse that forms stars. But G165 doesn't appear to be shaped by gravity. Not yet, at least. To explain what was observed, the research team ran magnetohydrodynamic simulations which combined the physics of gas dynamics with the influence of magnetic fields. These simulations showed that supersonic turbulence interacting with magnetic fields can produce the kinds of structures seen in it without the need for gravitational forces. This finding shifts the timeline for how we think structure begins. Instead of being initiated by gravity, some of the early organization in gas clouds might result from internal dynamics, especially in isolated environments like galactic halos. The simulations also reproduce specific observational features, asymmetric density profiles, multilayered velocity structures, and line width distributions that match those recorded by FAST. This consistency strengthens the argument that turbulence and magnetism can work together to sculpt interstellar gas. It also suggests we may be underestimating the influence of magnetic fields. In many parts of astrophysics, magnetism is acknowledged, but not always treated as a primary force. Observations like these push us to reconsider that assumption, especially in regions not yet dominated by gravitational collapse. In the bigger picture, it may represent a stage in the preparation of material for star formation. The filamentary structure it displays could be an early framework, an intermediate step between diffuse gas and dense star-forming clouds. Whether this process is common or rare remains to be seen, but the fact that it appears so clearly and it means we should start looking for similar features elsewhere, especially in regions we previously assumed were quiet or featureless. Implications in what's next. The Milky Way constantly exchanges material between its core and its outer halo. Some gas flows inward, fueling star formation. Other material is expelled, recycled, or suspended in the halo for long periods. Very high-velocity clouds like G165 could be part of the inflow acting as delivery systems for star-forming material. If filamentary structuring is widespread in these clouds, it might help explain how gas gets funneled efficiently into more active regions of the galaxy. Organized structures like filaments can guide the movement of matter, allowing denser regions to form more easily when conditions change. And because these features can form before gravity becomes dominant, they could accelerate the timeline for how quickly a cloud becomes star-forming. That means magnetism and motion aren't just shaping the gas, they're shaping galactic evolution. The discovery also highlights the importance of high-resolution radio astronomy. Instruments like fast and future arrays like the Square Kilometre Array are essential for resolving these fine structures. Without that kind of detail, it might still appear featureless. This also opens a door to more cross-disciplinary work. Plasma physicists who study turbulence in controlled environments may have useful models to offer. Astrophysicists working on galaxy evolution now have new parameters to consider, and data scientists developing tools for structure detection in large datasets will be key to scaling up this kind of research. Looking ahead, researchers plan to apply similar analysis techniques to other VHVCs. If clouds like G165 are common in the galactic halo, we may be on the verge of mapping a hidden architecture of pre-structured gas around our galaxy. Outro here, motion and magnetism shape structure quietly without stars or explosions. It hints that complexity in space begins earlier and more subtly than we thought. As we study more clouds like G65, we may rewrite how the universe builds itself. Keep watching. Thanks for watching. Cool.